In 2006, researchers noticed something strange. Atmospheric methane levels suddenly jumped by an unusual amount. Methane, CH, is a powerful greenhouse gas. Even tiny increases can heat the planet significantly. It traps roughly 86 times more heat than CO over 20 years. Scientists scratched their heads. No obvious new factories or coal mines suddenly appeared, yet methane was spiking. Ice core records show that methane naturally peaks at the ends of ice ages, roughly every approximately 100,000 years or so. But our last ice age ended about 12,000 years ago, and Earth's climate has been unusually stable, the Holocene, ever since. The 2006 surge had none of the usual suspects. It wasn't a big war, disaster, or industry boom, so it stood out as a puzzle. In other words, the atmosphere suddenly got more methane and scientists didn't know why. It took years of investigation using everything from ice core chemistry to space satellites to piece the story together. Ice cores drilled from Antarctic and Greenland glaciers are like time machines. Each annual layer traps tiny bubbles of ancient air, allowing reconstruction of past greenhouse gas levels. Through these cores, scientists see the dance of ice ages over hundreds of thousands of years. Each major ice age termination, the shift from a glacial to a warm interglacial period, has a characteristic methane pattern. In fact, ice cores show three distinct phases during terminations. Gradual greenhouse rise. Over millennia, CH concentrations creep upward, slowly warming the climate. Methane pulse. Then comes a sudden spike in methane over a few decades, which triggers an abrupt jump in temperatures to stabilize warmth. After the pulse, concentrations and climate settle into the new warm and glacial state for thousands of years. These phases appear repeatedly in the ice core record, which extends at least 800,000 years. The 2006 spike looked eerily like the abrupt phase 2 of a termination event. But we are not actually at the end of an ice age today. This raised the tantalizing question, was something trying to trigger another termination now? Milankovitch cycles, Earth's climate clock. Long-term climate cycles on Earth are largely driven by subtle changes in our planet's orbit and tilt. The Milankovitch cycles. These include orbital shape, eccentricity. Over approximately 100,000 years, Earth's orbit oscillates between more circular and more elliptical. A more elliptical orbit means bigger differences in solar energy at different times of year. Axial tilt, obliquity. Earth's tilt swings between about 22.1 degrees and 24.5 degrees on an approximately 4100 year cycle. A greater tilt makes summers hotter, especially at the poles, which melts ice sheets faster. Axial wobble, precession. Over approximately 23,000 years, Earth's rotation axis wobbles like a top, changing the timing of the seasons relative to perihelion, aphelion. In combination, these cycles change how much sunlight reaches high latitudes. When northern hemisphere summers become much hotter, due to a particular alignment of these cycles, ice ages tend to end. Conversely, cooler summers let ice build up again. In short, Milankovitch cycles pace the ice ages and interglacials. Our current warm period, the Holocene, began about 12,000 years ago when these cycles lined up for melting. However, by itself, Milankovitch forcing is relatively weak. Greenhouse feedbacks like CO and CO increase it, amplify the effect of a little extra sunlight into full deglaciation. Methane's potency, a fiery blanket. Even though methane is much rarer than CO, it punches far above its weight. Per molecule, air absorbs infrared radiation far more effectively than CO. About 80 times more heat trapping in the 20 years after release, though it only stays in. The atmosphere approximates in years on average versus centuries for CO. In effect, methane acts like a thin but powerful heat blanket around the Earth, a bit like wrapping a growing fire with extra insulation. Small additions of methane cause rapid warming spikes, which in Earth's history have been enough to transform frozen tundra into lush landscapes, even hippo-roamed savannas, in a matter of centuries. Detecting methane. From ice cores to satellites. To understand the 2006 mystery, scientists have employed every tool. Ice cores tell us the baseline, but we also need real-time data. Modern instruments include aircraft and remote sensors that can sniff methane plumes on the ground, and now even space-based spectrometers. For example, NASA's new super-emitters instrument aboard the International Space Station uses infrared lasers tuned to methane spectral fingerprint. It sweeps vast swaths of the planet every 90 minutes, pinpointing methane leaks down to the scale of a single facility. In effect, the super-emitter is an ultra-sensitive methane camera scanning deserts and industrial regions. This high-tech lens has already revealed many sources that were previously missed by ground surveys. NASA's spaceborne sensor even caught a 2-mile-long methane jet streaming from an oil field near Carlsbad, New Mexico. The leak was huge, on the order of 18,300 kilograms of CH4 per hour. About 40,300 pounds-hour. That flow alone rivals some of America's worst leaks, similar to the 2015 Aliso Canyon blowout in California. Such super-emitters underscore that a single large leak can make a big dent in global methane levels. In another case, EME emit 12 simultaneous plumes drifting west from gas fields east of Hazar, Turkmenistan. Some of these individually stretch over 20-30 miles. Altogether, they emit on the order of 50,400 kilograms of CH4 per hour, comparable to the massive U.S. blowout. This cluster was unexpected and had gone unnoticed by earlier surveys, showing the value of continuous global monitoring. Space data also flagged an enormous leak over a waste processing plant south of Tehran. This landfill plume spans about 4.8 kilometers, 3 miles, and was belching roughly 8,500 kilograms of methane per hour into the atmosphere. Landfills are a potent source of methane from rotting organic matter, and this discovery reveals they can be super-emitters on par with oil fields. In fact, capturing landfill methane by flaring or using it for energy is now a recommended mitigation step to prevent it from reaching the air. In summary, satellites have mapped dozens of major methane sources worldwide.
NASA Administrator Bill Nelson emphasizes that reining in methane emissions is key to limiting global warming, and instruments like EMIT are now helping us find where to plug the leaks.
Where exactly is all the new methane coming from? Researchers have broken it down into human and natural origins. Studies consistently point to leaks and vents in the global oil and gas industry as a major driver of the recent rise. A 2018 NASA-led analysis found oil and gas responsible for the single largest portion of the upward trend, about 17 teragrams per year. The shale gas boom, with many poorly sealed wells and pipeline vents, correlates with the methane jump. Unburned natural gas released directly to air is nearly pure methane. Equally important are biological sources. In the late 2000s, 2010 elves. Scientists noticed tropical wetlands in Africa and Southeast Asia were releasing more methane. Warmer temperatures and changing rainfall have expanded swampy areas and vegetation, accelerating microbial decomposition that emits CHO. Recent studies suggest this natural feedback may account for much of the unexplained increase after 2006. Livestock, cow burps, rice paddies, landfills, and man-made reservoirs are other methane factories. These sources have contributed steadily, but had not sharply surged in 2006. In fact, when scientists first added up all known sources, fossil fuel leaks plus wetlands plus farm emissions, the total exceeded what was actually measured, until they realized one more factor was at play. It turns out wildfires had temporarily decreased in the 2006-2014 period, partly offsetting methane emissions from biomass burning. Reduced burning due to fire suppression actually meant less CHA from fires than before, about 4 TGK lower, which helped explain why total emissions matched observations once accounted for. Putting it all together, the 2018 NASA study concluded the puzzle. Roughly 17 TGHE year of the methane rise came from oil gas, 12 TJ from wetlands rise, and a 4 T decrease in fires. In short, both human activity and natural feedbacks have been important, but pinpointing the exact shares remains an active research area. This sudden methane surge carries a sobering message. In past terminations, vast frozen landscapes, like northern peatlands and tundra, release methane and carbon, helping flip the climate warm. Today, although Earth isn't in an ice age, the rate of methane rise is unprecedented in the modern record. Some scientists warn we may be witnessing a mini-termination event, or at least the start of one. With enough added methane, the climate could shift sharply. However, it's far from certain. As Dr. Yuan Nisbet cautions, we have no exact historical analog for a post-ice age spike so soon after deglaciation.
So we can't say we've got proof, but we're raising the question of what might come.
Even if the current surge turns out to be a natural blip, it sounds a warning. Methane in the air today lasts only about a decade, so if we stop emitting more, levels will quickly come down, unlike CO2, which stays centuries. That means cutting human methane leaks now can cool the planet quickly. In fact, experts emphasize that tackling methane is a low-hanging fruit.
We can do a great deal to bring down methane, Nisbet notes, by plugging gas well leaks and managing waste, manure, and rice fields more carefully.
Every kilogram of methane we prevent from reaching the air helps blunt the fast-warming punch it delivers. In conclusion, the 2006 methane surge has turned into an urgent detective story. Satellite maps and isotopic analyses are revealing who's to blame, while climate records remind us of the stakes. Whether this event heralds a new phase of warming or not, the signal is clear. Methane matters. Finding and fixing methane leaks worldwide, from oil rigs to rice paddies, is a crucial and doable step in stabilizing our climate. Sources: recent research and news reports on atmospheric methane trends. NASA JPL mission data on methane super-emitters. And NASA science summaries of orbital cycles.